everyone, how's it going? My name is Liz from the Definity Foundation, and welcome to Community Conversations. This is an opportunity for you, the community, to hear from contributors in the internet computer ecosystem, as well as ask them questions live. The ledger Canister maintains the information on ICP balances and keeps a ledger of all ICP transactions. In this presentation, Senior Researcher Bogdan Warinschi will go over the design of the canister and describe ongoing plans for the development of the canister. I'll pass things over to Bogdan to explain more. Thanks, Bogdan.
Thanks, Liz. So I'm guessing that people attending already have the context, but just as a reminder, the internet computer is kind of powered by a utility token called the ICP token. And you would need this kind of tokens if you want to participate in governance. And you also need these tokens to be able to purchase cycles, which in turn are used to pay for resources used by Canister smart contracts running on the IC. So in this talk, I want to do just two things. So give a high-level overview of some of the concepts that underlie the ledger canister. This is the canister that essentially, as Liz described already, is the canister that keeps track of where tokens are, who has how many tokens. So I'm going to give an overview of these concepts, and then I'm going to describe a little bit of the ongoing work going over short and medium-term plans. So the ledger canister is essentially records a mapping between accounts and ICP token balances. So who can have an account on the ledger canister? To have an account on the ledger canister, you need to be an IC principal. That is, you need to be an entity which the internet computer can authenticate. So if you are a principal, then by default, you can have an IC ledger canister account. So the ledger canister will maintain information about the balances, like as I described earlier, who has how many ICP tokens, and will also allow owners of accounts to transfer ICP tokens from one account to another account. The ledger canister will record all such operations that affect the balances, and it will do so by maintaining a so-called transaction ledger. And right now, there's like three kinds of operations that change balances, and these are transferring between accounts, minting tokens to accounts, and burning tokens from accounts. So right off the bat, I want to kind of emphasize that when we're designing the ledger canister, we try to keep it as simple as possible. So in particular, we discussed following the ERC20 standard for tokens, but we felt at the time that it is too complex and it is a functionality that can be added on top of the token that we have already designed and implemented. Furthermore, we tried quite hard, and we didn't succeed to 100%, to keep the ledger canister agnostic of all other canisters. So the ledger canister is part of the NNS. In the design, we try to make the ledger agnostic of this fact, but yeah, we didn't entirely succeed. So just to put things a little bit in context, like to put in context my presentation. So who talks to the ledger canister nowadays? So on the one hand, we have the users that talk to the ledger canister using DFX. And for DFX, the ledger has one set of interfaces. Then there's the Rosetta nodes. I'm not going to go into too many details about Rosetta nodes. The Rosetta nodes, but I'm going to give a high level description of what these are. So Rosetta nodes are ledger canister clients, which can be run externally to the IC. And their raison d'etre is to essentially mirror the state of the ledger canister in the trust domain where they are being run, number one. And number two, allow whoever is running the Rosetta node to interact with the ledger canister. So why would you need the Rosetta node? So you may know that Rosetta, this Rosetta the Rosetta API is a Coin-based standard. So essentially, this is kind of a domain-specific language, which allows anyone to talk to a blockchain in a way that abstracts away from the details of the blockchain itself. So if I run a Rosetta node, I can interact with the ledger canister using generic concepts like blocks, transactions, and whatnot. But I do not need to know exactly how the communication between the Rosetta node and the ledger canister in this case is implemented. So the ledger canister for the Rosetta node offers an interface which uses protobuf for the communication. Then there's canisters that may already talk to the ledger, maybe not do much at the moment, but they can talk to it. Right now we're in the process of defining a candid interface for communication with the ledger canister, and in particular, this is the interface that I'm gonna kind of informs the terms that I'm using today. So I guess this is one can argue that the communication that between the effects and the ledger canister and between the Rosetta node and the ledger canister is kind of internal to the system, and so those interfaces they exist, but one cannot rely on them that they are not going to change in unpredictable ways. Whereas for the kind of interface that we're designing, we aim to provide backwards compatibility changes in perpetuity. So I'm gonna what I'm describing is essentially a fragment of this candid interface. All right, so here's kind of the starting concepts that underlie the ledger canister. So so the ledger canister maintains this mapping between accounts and balances. Who can have accounts? Principals. So one principal can control more than one account. So each account is controlled by precisely one principal, but one principal can control more than one account. We are going to distinguish between these the different accounts controlled by a principal using a sub-account identifier. So this is just a 32-byte string, which combined with the principal identity results into 28-byte account identifier. And perhaps confusingly, we also have a ledger address, which is essentially the account identifier to which we add some redundancy information. So what I just described is summarized in this informal equations. So given a principal and a sub-account identifier, we derive the account identifier. So this is essentially the account which will hold tokens. And given an account identifier, we add redundancy to obtain the ledger address. So a bit more specific. So here's how the account identifier is calculated. So given the principal and given the sub-account identifier, the account identifier is just a hash function SHA-224 applied to the concatenation of the principal and sub-account identifier prepended by a domain separator, a specific domain separator. Given an account identifier, we computed the address associated to it by prepending to it redundancy information, which is just some CRC code calculated on the account identifier itself. So here's these two concepts in action. So these are some accounts that exist on the ledger, and they're kind of special. So the first account that I want to mention is what we call the minting account. So this is an account of the governance canister, and is the account that corresponds to the sub-account identifier, the all zero string. The governance canister also maintains essentially all neuron accounts. So it's the controller of all neuron accounts. And there's these accounts take several forms. So the sub-account identifiers take several forms. So two of them I indicate here. So for example, there's one type of neurons for which the sub-account identifier is calculated by hashing the controller of the neuron together with some random string. And there's also some other neurons for which the subaccount identifier is just a random string. In the remainder of the talk, the minting account will play a role. The neuron account I just thought I'd mention so that it's clear that the ledger maintains this neuron information, neuron balances information. So we have this set of accounts, so mapping accounts to balances. The balances are changed by 3 operations. I already spelled them earlier, but here's how they look with some parameters. So the operations that act on balances are transferring from some source account to some destination account a certain amount and paying a fee. There's minting to a certain account a certain amount, and then there's burning from a specified account a certain amount. So these operations are the operations that act on balances, but when we record them in the ledger, we include them in a transaction. So they'll be part of a transaction, and each operation will be part of a single transaction. The transaction includes, besides the operation, will also include a memo field. This is just a 64-bit unsigned integer that can be specified, as we'll see immediately by the creator of the transaction. And also, the transaction includes a created at time field. This is just a timestamp which indicates the time at which the transaction was created on the sender's side. So not the time at which the transaction is recorded on the ledger, but it's the time at which the transaction was created on the sender side. And if you wonder why do we need to distinguish between these 2 points in time, this is useful for when signing transactions is done out of band, so it's done using cold storage, because a transaction is created at some point, then I take a break, I go and I sign it, and then when I come back, the time that I submit the transaction is different from the time that I actually created the transaction. So transactions are going to be recorded in the ledger, but before we record them, we include them in the block. So in some sense, blocks on the in the ledger canister are a little bit degenerate because each block will include a single transaction. So in addition to the information that that I described earlier, so the transaction, operation, memo, created at time, the block also includes a timestamp. This is the time. This is the time at which the block has actually been written to the ledger, and a parent hash. And I'm going to explain what this parent hash is in just a little bit. Essentially, this is what helps us chain the transactions together. So finally, the ledger is simply a list of blocks, and these blocks are chained together, as I'm going to explain on the next slide. So, so to explain this chaining, I'm going to just assume that that the ledger at some point contains blocks B0, B1, Bn. These blocks satisfy the following invariant. So if block Pi contains a transaction Ti, some hash information Hi, and some timestamp Ti, then it must be the case that Hi is essentially the hash of the previous block. So this is what changed the blocks together. Essentially, if I give you, or if you get a handle on the hash of the last block, which is what we call the last hash, and which is also information maintained in the ledger, this value last hash essentially commits to the entire ledger if the hash function used is collision resistant. And this is going to be important a little bit later in this presentation. So now, how do I add a new transaction to the ledger? So I'm given transaction T. What I'm going to do is I'm going to construct the new block Bn plus 1 by putting together the transaction that I need to add. The last hash, remember, is just the hash of the previous block that existed already in the chain. And we added the timestamp now, which is the time that the ledger canister sees when it makes this system call. Then essentially we add bn+1 to the list of transactions, to the list of blocks, and we calculate the last hash now to be the hash of the blocks that we have just added. All right, so this is abstractly, this is how the transaction ledger is constructed. Now, how do we calculate balances? So balances obviously change as we add blocks. The balances change. So I'd like to say in the obvious way, and I think that this part is not rocket science. I'll just give you the kind of the formal description and highlight a couple of things. So this is a recursive definition for the function balance given a ledger of a certain account. So what is the balance of account ID given a transaction ledger? So this is defined recursively as follows. If the transaction ledger is empty, then the associated balance is 0. Otherwise, otherwise the ledger is not empty. So the ledger looks like there's a bunch of older blocks, and then there's the last block. Then the balance of account ID given this state of the ledger is whatever balance the account had after we have processed all of the blocks but the last one. And now, depending on what the last block is, we change the associated balance. So if the last block is either minting funds to the account ID or is transferring funds to the account ID, then the balance is whatever the balance was before the last block plus the amount that is minted to the account or transferred to the account. If the last block is transferring a certain amount from the account, so from the account that I'm interested in, then the balance of this account after I've added the block to the ledger is whatever balance it had after I have added all of the previous blocks but the last one, minus the amount that is transferred from that account minus the fee. So this is one thing that I wanted to highlight, namely that essentially the sender pays the fees of associated to a transfer. Finally, burning is similar, right? So burning, if the last block in the ledger is burning funds from a certain account, then the balance of that account is whatever the balance was after processing all of the blocks but the last one minus the amount that is specified to be burned from that account. And otherwise, so if this block does not involve this account ID, so it doesn't mean to burn from or transfer to or from, then the balance is whatever balance the account had up to this point. All right, so this is kind of the internal state of the ledger. So the internal state of the ledger is essentially a collection of blocks and the mapping of accounts to balances. So this is, now I'm going to describe the way in which we actually push transactions into the ledger. So this is done by invoking a method called transfer, and the signature of the method is as follows. So whoever calls the method needs to specify an amount of ICP to be transferred, a fee of ICP to be paid, needs to specify which sub-account of the caller should be used from transferring funds from, needs to specify to what address of the ledger the funds should go to, can specify, well, it needs to specify a memo field. This is just as I said, an arbitrary unsigned 64-bit integers, which can be used for business logic or for whoever uses the ledger. and may specify a created at time, as I described a bit earlier. So specifying the sub account and created time are optional, but I'm gonna explain how the ledger behaves with respect to if these are not specified. So next, I'm going to describe the semantics of transfer. So a caller makes the transfer call, provides these parameters. Now, what happens in the ledger? So first, the ledger calculates the source account from which the funds to be transferred. So this is just the account identifier associated to the caller of whoever calls transfer, and the sub account that is specified. So if no sub account is specified, then the sub account information used here is going to be the all zero string. So I'm gonna refer to this account like as the default account of the caller. So for example, the default account of the governance canister, if you remember, is the minting account. Then the ledger checks if the fee that is specified matches the fee that the ledger expects. So currently this is 10 to the -4 ICP. And then it performs some checks on the created at. So first of all, if created at is not specified, then it is set to now, so the time that the ledger canister sees. And in other case, afterwards, it does the following checks. So first, it checks that the created at time is not too far in the past. So that means specifically, it checks that created at time is not smaller than now -24 hours, and it also checks that it's not too far in the future. So it checks that if there is any drift, it should not be bigger than 60 seconds. So if this is false, then the transaction is rejected, the call is rejected. If this is true, then we check that there is no duplicate transactions since the timestamp created at time. So remember, there's this window which is at most 24 hours, within which we check if there's one transaction which already has a specific created at time specified with precisely the same source, destination, amount, and memo fields. If this is the case, then we reject the transaction as well. Then we also check that the source account has sufficient funds to cover the amount to be transferred plus the fee. And currently, and I'm going to talk about this a little bit later, we also check that the caller is not a canister. Actually, we check that the caller is not a non-NNS canister. So NNS canisters are allowed to use this interface, but arbitrary canisters right now are not. So if all of these checks succeed, then the transaction succeeds. So we add to the transaction ledger a block consisting of the parameters that have been specified in the call. So in this case, it's a transfer from account to account, amount, fee, memo specified, and created at time calculated, as I explained. And then we also update the balance information, and we return to the caller the index of the block in the transaction ledger. So we also use this. This is kind of partially true. I mean, we don't use precisely this method, but we use a method which is similar to this one, which was already implemented, and it is used between the communication between the governance and the ledger. But we use something like that to also implement minting and burning. So more specifically, when we call transfer, we check if the source account, so if the source account is not the minting account. That is, if the caller is the governance canister and the specified sub account is the all zero string, then this is the minting account. And then we interpret this, rather than a transfer, we interpret this as a minting operation. And the result is that we add to the transaction ledger a block containing the operation mint and its associated parameters, and we update the balance information accordingly. Conversely, we also use the same method to burn tokens. So while minting is a privileged operation because the caller must be the governance canister. Burning can be done by anyone, and it is simply done by transferring funds from an address to the address of the minting account address. So if the address is the minting account address, then we're gonna, the tokens that are being transferred will simply disappear. We have right now 2 restrictions, so not all calls like that will succeed. It must be the case that the fee that is specified is 0, and the amount that is burned is more than 10 to the minus 4 ICP. So if this is true, then we add to the transaction ledger the information that we have burned from the source account a certain amount, then we update the balance information. So informally I described how we calculate balances. So there'll be, well, there is already, but the candidate interface will also include the method balance of. So this method, when invoked with a ledger address, will return the balance of the associated account at the state at which the method is executed. All right, so I'm gonna kind of take, so this was kind of targeted to canister interaction in some sense. I'll say a few words about user to ledger canister interaction, and also Rosetta to the ledger canister interaction. So if you talk to the canister and you're a canister and you talk to the ledger canister, you are necessarily talking using replicated execution. So then if you make a query like balance of, what you'll get is a reply, and the reply will be guaranteed to be honest. Like it's the real, you'll get the real answer. But if you are a user, you may choose to talk to the ledger canister using unreplicated query calls. So for example, you can ask, so this just means you can ask just a single replica which hosts the ledger to give you the balance of an account, or as is the case of Rosetta nodes, to give you blocks, to give you the blocks from the ledger. So a Rosetta node, for example, will sync the entire ledger, so we'll need to get all of the blocks, and it will not do this by getting block by block via replicated call, because this would just take forever. So instead, it issues query calls and it gets the blocks fast, but now it needs to get it needs to somehow verify the authenticity of the blocks that it had obtained. So here's where this last hash that I was describing plays an important role. So remember, the transaction ledger is just a sequence of blocks. Each block contains the hash of the previous block, and the ledger canister also maintains this variable called last hash, which is essentially the hash of the last block in the ledger. So therefore, a commitment to the entire ledger content. So now, how can somebody external verify that what it obtained are the blocks from the ledger? So here we use this notion of certified variables. There's a nice talk about it by Joachim Breckner, which gives details, but at a high level, essentially, a canister can set a certified variable, and the effect is that in every round, the IC will produce a signature on the value of that certified variable. So then, in this case, for example, at every round, the IC signs the value of the last hash. So now, if I want to verify that the chain of blocks that I have obtained is genuine, so it is actually the blocks that are maintained by the ledger canister, it suffices to get the signature by the IC on the last hash, verify that the chaining is correct, and verify that signature on the last hash. All right. Right. So when we were designing the ledger canister, we thought we'd be facing this limit that where there's like two limits. One limit is the fact that the memory of that is available to a canister was limited to 4 gigabytes. Okay, in the meantime, it has been increased, but at the time we didn't know. And this is one issue. The second issue was that even if we had arbitrarily large amounts of space, it wasn't clear how to deal with upgrading, because upgrading goes through this step where you serialize the data that is in your canister. In serialization, a lot of data may take a lot of cycles, which in turn may hit some limits that the execution imposes. So then we thought we cannot keep the entire state of the ledger in the ledger canister itself. So we kind of shard it. So the ledger canister right now at any point maintains somewhere between 1,000 and 2,000 transactions. And then the moment it gathers more than 2,000 transactions, it sends the 1,000 oldest transactions that it has to an archive canister. So right now there's still one archive canister, and the bound, I think we set it to be 1 gigabit. So then 1 gigabyte. And then when this limit is hit, then we'll spawn out a new archive canister. All right, so this is a topic that I wanted to touch upon just because it is, I think there are some questions in the forum about it. So the ledger canister offers this, it's now a privileged method called notify. Essentially, notify allows somebody who transfers funds to a canister to ask the ledger to notify that canister of this incoming transfer. And this is useful, and we have used it in the past, for example, for creating neurons. So the idea would be, if I wanted to create a neuron, what I do is I transfer funds from my account to a neuron account, which is an account of the form that I have showed earlier. But an account needs to be an account that somehow is agreed in advance with the governance canister. And then I can ask the ledger canister to notify governance that I have transferred these funds. And then when the governance canister gets notified, it can create the information. It now knows that it needs to create a neuron for the funds that have been staked like that. We also use notify for converting ICP to cycles. So I guess the workflow is more or less, I transfer some funds to the cycles minting canister, and then I ask the ledger canister to notify the cycles minting that I have transferred these funds. And we use the memo field to encode either that the funds the cycles resulting in the transfer should be in the conversion should be used to top up a certain canister, or should be used to create a canister. So this is kind of convenient. It's a convenient mechanism, and it also relies quite kind of, if a canister gets notified by the ledger, it trusts that the ledger behaves honestly. And in particular, right now the ledger will not notify successfully twice the same canister with respect to the same transaction. So essentially, this prevents double spending. So if I transfer some funds and I notify a recipient of that fund, the ledger canister will only do this at most once. So it's convenient and it's useful, but unfortunately, it's one place where we kind of deviated from our purpose, our design goal of keeping things simple. And in particular, the fact that the ledger canister needs to maintain some state both internally and also at the system level regarding calls it made elsewhere adds a lot of complexity, and it needs the ledger canister to manage additional state. So it doesn't scale well, and it would not scale well. We don't see how it can scale well if we made this method available, widely available. So I'm gonna go quickly over some of our plans, and since I talked about notify, this is not really the order in which we do things, but since I talked about notify, I'll start with that. So we plan to deprecate notify. So right now it's not used to create neurons anymore. it is still used in these flows for converting ICPs to cycles. Yeah, so we're working on designs where this conversion will not use notify. And kind of to give you an idea of what you're thinking about is essentially managing the information about which transaction has been so which transaction has the recipient not been notified about. We want to push this management from the ledger canister to the recipient itself. So then the recipient would need to deal with this double spending issue. All right, so what are we working on now quite actively actually is first, we are working on removing this restriction that only self-authenticating principals, so that is not canisters, can transfer tokens. So we know that this is something that the community really wants. What kind of holds us back are two things. So I want to, I put this, I didn't use many colors, but I thought I should use this red here to say warning. We view this, even if we are gonna make it available in the short term, we view this as experimental, and there's at least two issues why this is the case. So one is, I guess one is a security issue. The other one is an availability issue. So the security issue is that we really need to make sure that canisters cannot impersonate other canisters. So if I have a canister that manages somehow ICP tokens, we really need to ensure that no other canisters can somehow either impersonate or tamper with the execution of this canister. And this is quite difficult right now because these canisters are run within, when executed, they're run within the same process and on separate threads, but each thread running some WASM execution environment. If there is some jailbreak that happens in one thread, we cannot guarantee that there's no interaction between canisters. So if I have a malicious canister running on the same network, on the same subnetwork with the canister that manages ICP, we cannot. The risk there is not zero at the moment. So this will be solved by the canister sandboxing work that is actually progressing quite nicely. And the last estimate I've heard is like 1 to 2 months we should have that. The second issue is one of fairness. So here the problem is that so each subnet. So how to put it? The communication between the canisters on one subnetwork and the ledger canister goes through a single stream, so a kind of a pipeline, where all of the queues, all of the outgoing queues of the sending canister or the canister I want to talk to the ledger canister are flattened, and so we flatten all the queues, put them in a stream, and send them across. So this, and there's not many fairness provisions about how do we trace these messages in the stream, which means that it is possible to run into a noisy neighbor problem where one canister that does sends a lot of messages to the ledger canister prevents not forever, but makes the latency of communication of with the ledger canister of other canisters increase maybe dramatically. So I think we'll be happy to declare this feature non-experimental once we solve at least these issues. So
hey,
together with, yeah.
Sorry to interrupt. We have a question in the chat. So community members asking, what would you recommend receivers replace notify with?
So we have some designs of protocols where, so it's not gonna be simple, but we have at least one verified design, verified meaning we did a formal methods analysis, and we verified that it works. So there's some protocol that you can run between the receiver, the sender, and the ledger. So very roughly, if I remember correctly, how it worked is something like the sender and the receiver do some sort of out-of-band communication where they agree on an invoice number, like a unique, a random number. And that random number is included in the memo that of the transaction. So I agree on the random number, then I make the transaction, I include that random number, and then I notify I talk directly to the recipient saying, I've sent you the transaction is at this height, and here's the invoice number that we have used. And at that point, the receiver knows that checks, then it knows that it's received, it knows that it must have the funds must correspond to the conversation that it had earlier with the sender, and then provide whatever service. And then you need to, the issue here is not you need to manage the state, because these invoices you need to keep to avoid double spending. You need to keep invoices for a while. So then some bounding, like what we do with notify, should be also added. I don't know if that was clear enough.
Yeah, no, I think that's helpful. And if you had asked this in the chat, and if you have any follow-up questions, feel free to do so, and I can field it over to Bogdan. But yeah, as you were, Bogdan.
All right. So so together with lifting this restriction, we want to make public the candid interface that I started describing. So I described the transfer and get balance, which on their own, maybe they're not particularly useful, because you also need a way of looking at the blocks. So right now we're working on an interface that would allow you to fetch blocks, and would also allow you to fetch this certification information, the signature and the last hash, if you were an external party and you needed it. So finally, balances, the way we implement it right now, balances are not certified, right? We only certify the transaction, the transaction ledger. So if I ask a replica, if I query a replica for a balance, then there's no guarantee that I get. So one can work around it first by either making a replicated query, or making multiple queries to multiple replicas. But we've been also discussing adding this information to the data that is being certified by the ledger canister. So then if you ask, give me the balance of a certain address, then you get the balance together with the certificate that the balance is what it is, or the state that is in the ledger at the time. So that's all I had. Thanks for your attention. And maybe I should open the chat to see the questions.
Yeah, no worries. I've noted them down, so I can pass those over to you, Bogdan. Thank you for your talk. Okay. First question: what is the state of removing the calls from Canister's test? Jens Groth mentioned some security issues on the forum. Have they been resolved?
Sorry, what's I didn't get the first part.
Oh, what is the state of removing the calls from Canister's test?
Calls from Canisters?
Test?
Test?
Yeah.
Is it in the Q&A section, or is it in the chat session?
It's in the chat. So for the person who asked this, if you want to clarify, that would be helpful. In the meantime, we can move on to some of the other questions. So next question: do I need to use the Rosetta API to interact with the Ledger Canister if I'm calling the Ledger Canister from another canister on the IC?
No, definitely not. So the Rosetta API is something which runs outside the IC, and it's something convenient to get a complete image of what's in the ledger. But if you're a canister and you need to talk to the ledger canister, you just call it directly. You do not go outside. I don't even see how you could do that.
Okay, great. Thank you, Bogdan. So our next question: is there an interface documentation for the Ledger Canister with its canister ID, etc.? Do I need the DID file for the Ledger Canister in the DFX directory, or do I just need to send messages to the canister itself?
So we're working on documentation. So when we make the candid interface public, we'll also add documentation regarding how to access the Ledger Canister, how calls look, how to construct calls, the identity of the Ledger Canister. This is I think it's, if you ask on the forum, somebody will give you the identity of the ledger canister. I don't know it off the top of my head, but so all of this will be documented.
Okay, great. And probably a follow-up to what you're saying, we have a chat from the community members saying, as a network engineer, I'd love to see a much deeper dive on the networking protocols than what is on the website. Will there be more docs, and also when are they coming?
So I know there'll be more docs. I think there'll be a lot more docs coming. When, that's a little bit hard to tell. So for the, I think the question was about the general protocol, right? Not about the networking protocols. Yeah. So we have design. So we have documents for the design. We have documents for some of the design, I should say. We have a lot of slides. How we push that into the public, I don't really know. So I think it's more of on a case-by-case basis. But you know what? I think it's a good opportunity. If there is specific topics that you guys would like to see deep dives on, I think you just tell Liz, and then we'll make it happen.
Yeah, definitely. If you all have any sort of feedback in terms of what kind of docs you want to see, not even just limited to the topic at hand, we're always collecting feedback and we're always trying to get more stuff out there. So, so yeah, definitely let us know. Okay, so Bogdan, next question. Is there a way to get transaction history for a particular address, like all transfers to and from an account?
Well, you can use ICROX, I guess. But if you want to do it by yourself, one way to do it is run a Rosetta node. The Rosetta node will give you a database of all transactions, and then it's just a linear search. I think we actually do plan to add this particular feature to the Rosetta node itself. Right now, it's not. Right now, the Rosetta node will download all transactions. We'll put them in the SQL database, but unfortunately, it's their protocol, their protobuf encodings of the blocks. So which doesn't make it searchable. So one of the, I think it's even a short-term plan, is to make that database searchable, and then you could do what you wanted by running your own copy of the Rosetta node.
Okay, excellent. So Bogdan, next question. Is there a way that the ledger canister could ever become compromised?
Yeah, so I can give you one way. For example, if enough node providers collude to impersonate the ledger canisters, in theory, it's possible. I mean, you have to, first of all, you have to do this. You have to run go outside our trust assumptions, and one of our trust assumption is that this is what I just described is not possible, and there's always possibility of bugs in its software, right? So, and it's rather complex software. So we kind of do our best to keep the NNS canisters isolated, so they run on their own network. There's no malicious canisters potentially malicious canisters running alongside. So it's, yeah, there may be a way, but there's nothing obvious that comes to mind right now. The most obvious way right now is get node providers colluding.
Okay, thank you, Bogdan. So next question, can you expand on some of the differences between how the ledger is maintained with the Internet Computer versus other networks like Ethereum or Bitcoin?
So in some sense, our ledger canister essentially maintains a ledger on top of a ledger, right? Each sub network that runs on the that forms the IC runs a consensus protocol where they agree on what blocks should each replica execute. Now, this is deep down below. the canister itself, as I described, is maintaining this information replicated because the canister itself is replicated, and inside it maintains this chain of transactions, which resemble quite a bit actually the Bitcoin blockchain. Now, this is kind of in terms of technology, I guess there's some similarity with Bitcoin, but I think the entire stack is kind of different. Yeah, I'm not sure how much more I could speculate here. So on Ethereum, the information is replicated on all about balances is replicated on all nodes. On the IC, the information is only replicated on the nodes that run the ledger canister. I guess that would be also a distinction, which is also what makes the IC more scalable.
Okay, no, that's definitely helpful. And as a follow-up question, what are some of the pros and cons of the design that the internet computer has versus some of the other networks that we just talked about?
You mean in terms of the ledger canister or tokens, or?
Right. Yeah, ledger canister.
So I guess on the one hand, our tokens are simple. Maybe one can say simplistic because you have to go through some hoops to use them. Whereas other tokens, so Ethereum has this more advanced versions of tokens, ERC20, and there's some other standards. Right, we are kind of 5 months from launch. I think our token would, you can embellish our token by, as I described earlier, by adding additional canisters, which would add additional functionality to the tokens. But yeah, it's still, I guess we're still designing, we're still working towards so I see Ethereum and ICP are quite different. I just saw a comment.
Yeah, that's true. That's like a comment from somebody in the chat, and I agree. I think that there are some like, core similarities in the sense that they're both blockchain platforms, but I think in terms of the design and implementation, and also in terms of potential use cases down the line, I do think it's quite different. Cool. So Bogdan, moving on to the next question. The notify function in Ledger requires that the from and to of the previous transaction, the block height, is equal to the from and to of the transaction that calls notify now. This is done for safety. I don't understand why you don't put this check in the notify target canister. That way you can get the same security and more flexibility.
I think this is kind of what we want to, where we want to move to. So we want to put the check in the check regarding the transfer would be done in the receiving, in the canister that receives the funds.
Okay, as in that is what should be done, or can you clarify?
This is kind of the design that we're kind of going towards. So we want to actually remove the checks. We want to remove well, actually, there's a spectrum of possibilities, like completely remove notify, or still maintain notify on the ledger, but do the maintain the information about what has been notified in the target. Maybe this is what I don't know who was saying that. If I understood correctly, then this is one possible design that we're going to. Okay. There's another design where you completely remove notify from the ledger.
Okay, I think that makes sense. Thank you for clarifying, Bogdan. So we have our last question for today. So make sure to get your questions in if you do have any more burning questions for Bogdan. So the question is, and this might be a little bit out of skip, so Bogdan, if there's different forum in which this question should be answered, definitely feel free to say that. So unclaimed Genesis neurons are going to be swept in a month or so. What will happen to them?
Oh, I don't know. I've heard about it, but I don't know about those plans.
Okay.
Yeah. Sorry.
No, that's a completely fair answer. And for the community member who asked this, maybe you can ask in the developer forum or on the Reddit, and someone else can get back to you. Okay.
I think on the forum, on the developer forum is probably
you'll
get an answer faster, I think, because we are pinged, whereas on Reddit we're not always pinged.
No, that definitely makes sense. Cool. So thank you everyone for your time on this community conversation. Thank you, Bogdan, for preparing this very thorough and helpful presentation, and see you all at a future community conversation. Bye, everyone.
Bye.